So your exam will have 6 problems, much like the review, except instead of having the first problem first, as was in the review, which is last year's exam, I put that it's not a multiple choice, it's more like a short answer and fill in the blanks. I put that last, and that's worth only 7 points of your grade out of 100. And so we're going to start with calculus, parametrized curves, and polar coordinates. So this is going to be the first problem on the test. You'll have 2 parts. Next is some conic section questions. So conic sections is where we start looking at parabolas and hyperbolas and stuff. So this is probably where you're going to need to complete the square if you need to go there. Vectors, some vector problems. So basic vector operations, arithmetic, including dot products and some applications like finding angles between curves and areas and volumes and projections and stuff. Number 4 would be lines and planes, equivalent to finding distances of things. Number 5 is the Fernet frame, and I've kind of mixed in a projectile along the way. So you can imagine like a curve that you're following. You can find a Fernet frame from that curve, and then from that curve you get ejected off and it becomes a projectile problem. And so similar to the projectile problems that we've been doing. And then the last one, instead of a multiple choice that I had as a first problem on the last year's exam, it's a short answer and fill in the blanks. And so it's going to ask you for formulas of things. It's going to ask you how to compute certain things. It's going to ask you to fill in the blank of stuff. So I think if you have a good handle on the review, then you should be okay on the test. And the way I kind of categorize okay is by grade level. So I think I mentioned if you can do all the problems on the review without needing much help, I think you're at a good C level on the test. And then if you know how to do the homework problems and the quiz problems, then you're probably at a good B+ level on the test. And if you know how to do the review and the homework and the quizzes, and you understand everything that was done in lecture, then you're probably at the A level. And understanding means different things to different people, and that's why when they talk about rubrics and student learning outcomes and assessing students from an outcome point of view, they never use the word understand, because understand is too vague. So to me, understand means you're able to do the computations, but you also know the background work to the computations that you're doing. Like a simple example would be, you know how to take the dot product, but what is the dot product used for? Well, you can use it to find an angle between 2 points. You can use it to find work. You can use it to find whatever other applications we've talked about. Okay. Last year's exam, I made the multiple choice worth like 20 points, but like I said, I shifted the multiple choice to a short answer, fill in the blanks, and I moved that last, and that's only worth a few points. I think it was 7 or 8 points. So your main focus should be on the first 5 problems on the test. So your main focus should be getting those problems done. They're worth a lot more points, and and you need to focus on that business first. I'm going to pass this back. This is all right. Any questions about the layout of the exam? Yeah. Well, I don't know how early we could start. So class is supposed to start at 45, so maybe 5 minutes earlier. I have a class that ends at 12:25, but I was going to say 12:30, but then there's people that are not going to be able to make it because they have class somewhere else, and so that wouldn't be fair time sharing with them. So I think 12:40 would probably be a good start time, so 5 minutes earlier. And like I said, I purposely made this last problem shorter and less points, so to give you guys more time. I had like 15 or something questions on that one, and I had it first problem, and then I was talking to my wife about it, and she said, she's always saying, be nice to your students. And I said, I don't want to be nice to my students.
So you rejected it as a try?
Well, I found a compromise. So her suggestion was just to eliminate that problem. And instead of fully eliminating it, I moved it last and I made it less points. So your focus, the majority of the points, at least 90 points, is based on these first 5 problems. So you focus on that, and then you work on the short answer stuff. Okay? So I think that was a good compromise. All right. So our task today is to look at the review sheet and go over these problems in the review sheet to see how well we know it. Now, I'm hoping that you've already tried this at home, because otherwise it'd just be like lecture, you know, new things, and then you're just following along, and just because you're doing what I'm doing and you didn't think about this stuff on your own doesn't mean that you know this material. Remember, being able to do the review sheet on your own puts you at about a C level, right, on this exam. And so if you don't know how to do this on your own, and you're just going to base it on what we're going to do today, then you're kind of already a step behind. And so that doesn't help you with your test much. But I asked you guys to see if you can look at it yesterday so that you'll come to class with some background on these problems already. So that will be, I think that would be more helpful. All right, I'm going to skip over the first one and just jump to the calculations and then come back to the first problem. So let's do these. These problems where you have to find things and graph things and stuff. It looks like I'm going to need my calculator too. So I'm going to use my calculator like you should be using your calculator instead of using my easy programs to be able to graph things. Just to remind you of how to graph parametric equations and polar coordinates and stuff like that on your calculator. Ooh. All right. The first problem is find the slope of the tangent line to the curve at a given point, and this is your graph, and then you have to plot it. So slope of the tangent line. So I'm looking at finding an equation of a line, and it doesn't say that it has to be in parametric form. So I suppose you can do it in parametric form, but I'm looking more of a line in Cartesian coordinates that we learned back in algebra or wherever it was. So I need the slope and the point. And so to find the slope, I'm going to need to take the derivatives of things. And if you remember the formula for this, but you get a sheet of notes, right? And you can write down formulas, you can write down examples, you can draw pictures and diagrams, you can write yourself a poem so that you can be, I don't know. Yeah, just to calm yourself down, a little prayer, a little mantra, whatever will help you with your test. Or a picture of somebody that would motivate you to do well on the test. Picture of Leibniz or Newton, I don't know. I didn't want to go there, but okay, so it's dy dt over dx dt. It's like dy dx is your slope, and in terms of polar coordinates or in terms of parametric equations, you would say dy dt and dx dt. So you find the derivative of each one. I got a 3t squared plus 6 for the first one. That's dx dt. I already got it wrong. And then the dy dt is 2 minus 2t. And we want to evaluate this when t is equal to 1. So I think this is going to give me a 0 on top. And if it gives a 0 on the bottom, then you're kind of in trouble, and you have to graph it to see what's going on. But it's non-zero on the bottom, right? Negative, positive 9 or something. Anyways, it's 0, so your slope is 0. And if your slope is 0, you know that your x doesn't matter. It's just your y value that's important. But you can plug in a point in the slope too. But in this case, when t is equal to 1, we got your x is equal to, let's put 1 in there. You get 1, 6, 7 or something, 8. And then your 1 in here is 0, oh, 2, 1. So with your point and your slope, you have the equation of the line y minus y1 is equal to the slope times x minus x1. Again, because slope is 0, it doesn't really matter. Y is equal to 1 is your equation. And so we would graph it using our graphing calculator. So just to remind you on how to use the graphing calculator, you want to change your mode to a parametric equation. This is for TI 83 or 84, so if you have an 89, I'm hoping that you got a good handle on an 89, you know how to deal with it yourself, so you can change your mode there. Here I'm going to go to parametric equations. Now that it's in parametric equations, I have my x of t and y of t functions. So it looks like I have a t cubed plus 6t plus 1. That's my x. My y is 2t minus t squared. Now I can kind of blindly graph this and see how it might look like, but if I know that I have a point 8, comma 1 in my graph, I may be interested in having that kind of be the center point. So I would probably go to my window and adjust this accordingly. 1 is involved, t is equal to 1 is involved, so I probably want to go from 0 to 2 at least, and might be interested in going further. For now, let's just go from 0 to 2 and see what happens. And the t step, remember that was automatically adjusted to something. 0.1 might be enough. 0.05 is actually better. But remember, the smaller this number is, the longer it's going to take, because the graphing calculator is going to plot those points and connect it with lines. The x-min, so the x goes from, the 8 is my x value, so maybe just to put a good square around that, or a rectangle around that, I'm going to go from 0 to 16 just to double it. And then my scale, I can go by 2s. I guess the scale really doesn't matter. I'll go by 2s here. My y-min, my y includes the number 1, so I may want to go from 0 to 2, or maybe go even further, maybe go from -1 to 3 or something like that. So -1 to 3. And then scale is 1. So I think that's good enough. Let's see if we can take a look at the graph of this. So here's your graph. If you want to trace it, you're going to trace it according to, this is PL, plot 2, there it goes. So you're going to trace it according to the t-value. So as you move along your t-value, you're tracing your x and your y values. So I want to put t is equal to 1, so I'll just type 1 in and then enter, and that's going to give me my x value, which is 8, my y value, which is 1, and then that tells me what graph I'm doing. So that's how you would graph.
Now that question is just asking for the slope.
Oh, yeah, so I guess that would just be 0. So I went a little bit farther here. Okay. Say it again? Yeah, it does say graph it. But I actually went and found the equation of the line. So if I'm looking for the answer here, I guess the answer is this. Slope is 0. Maybe I should write that down. M equals 0. Box your answer. Do you guys box your answers? Mm-hmm. Okay, good. All right, any questions? Let's do the part B of this problem. Set up the integral. So notice it says set up the integral. When you see set up, that means don't do it. Don't compute the integral. If you have a TI-89, you can punch it in there, but if you have an 83, it's a little bit more difficult. You can use 83 to get a numerical value for your integral if you want. But I'm going to look, well, I already got the test printed, so I hope it all works out. I was going to say, I don't think I have you actually compute any of the integrals there. The more important thing is to be able to set up the integral. Set the integral to find the area of the region that's inside of the curve. So I have a couple of curves, it looks like, and outside of this curve. So I have to know what those look like. And so it says graph it last. Maybe you want to graph it first, and then that'll give me some ideas of what's going on. So now I have to change my mode from parametric to polar so that I can graph these things. So I'm going to go change my mode to polar coordinates, and then I'll put in R1 and R2 for my polar coordinate graphs. So it looks like I have a 1 plus the cosine of 2 times theta. And so this is the multi-purpose button over here. Depending on what mode you're in, it's going to choose the appropriate parameter. So that's one graph, and then I have another graph that's 2 minus sine of theta. It would be good, by the way, before you graph this thing, it would be good to get some idea of how this thing might look like. So this 1 plus cosine 2 theta Maybe I should have done that first to take a guess of how it might look like. If I look at this in terms of x and y, like r and theta, if I were to graph this as if it was Cartesian, it would be cosine of 2 theta, which is this, kind of shrunk down because of the 2, shrink it down, and then moved up 1. So if it moved up 1, then I notice that this thing is never going to be negative. It's going to go from 0 or from 2 to 0 back to 2, and this is only going from pi, from 0 to pi. So the actual graph of that, when theta is equal to 0, I'm at 2, and then it's going to shrink down when it gets to pi over 2, and then, let's see, I'm imagining my angle here, right? Going this way, at pi over 2, it's at 0, and now as I keep going to pi, it's going to go back to it's going to make that shape again. So it looks like it's going to go and do this kind of move on this to pi, and then if I keep following this along to 2 pi, it looks like it's going to redo the same shape. So I think this is going to be an infinity sign, a sideways 8. So that's my guess for now, and we'll confirm it when we actually look at the computer, the calculator. Now for the other graph, this is 2, so I have a sine function, and then it's reflected. Oh, I don't know if I can reflect this. Yeah, it's kind of reflected. No, that wasn't a reflection. Can I do this? No, I can't reflect it. Oh well. So let's reflect the sine function. So that's negative sine, and then it goes up by 2 units. So by 2 units, here I don't even go to 0, so it looks like it's always going to be far away. So I'm thinking of this more like a cardioid now, a heart shape that doesn't have any loops, it doesn't hit the origin. So let's see how this kind of looks like in your graph. At 0, you're at 3. This is 1, this is 2. You're at 2, right? 1, 2, 3. So you're at 2. So you're starting at the same spot, I think. And then as you go further, you're going to go down to 1 by the time you get to, let's see, by the time you get to pi over 2, you're going to be at 1. So this is going to go around over here. By the time you get to pi over 2, you're going to be at 1. So this is 2, maybe 1 is over here. And then you go back up to 2. So you go back up to 2. And then over here until you get to 3 pi over 2, you're going to be at the maximum of 3. So when you rotate your drawing arrow to here, you're going to be at 3. And then you're going to connect. So I think this is how the graph is going to look like. Those are the 2 graphs. Or maybe this goes in. I don't know how it's going to look like. Well, we'll see. But you should try to get some idea before you actually graph it. Get some idea how it looks like. So it looks like based on this, I'm going to need my window to be adjusted properly. I want it centered at the origin, it looks like. Maybe I want my, my theta to go from 0 to 2 pi, and my x to go from -2, maybe -3 to 3. And then my x scale, let's just put 1 in there, so if I need to look at the tick marks. My y min has to go below -3, so it should go negative at least 4. And then I can have my y max to go all the way up to 4 also, or I can have it less because this thing goes only as far as maybe 1 or 2. So, but let's make it go all the way up to 4. And then that's it. Let's see if we can draw it out. So remember, because of the way you adjusted your window, this thing might look like it's flattened out, so it's not going to be drawn, to scale. All right, so it makes it hard to see. Let's see if we can zoom in. So we want to find the area of the region that lies inside of the figure 8 and outside of the other curve. So inside of the figure 8 and outside, it might be over here, and it really looks like it's going to be hard to see. So I may want to zoom in. Let's zoom in, and you get a chance to figure out where you want to zoom in, and the default is 0, 0, or the middle of the screen. So I'm moving my cursor. It's really, really small over there, that little X. I'm moving my cursor closer to this spot, because that's where I want to zoom in. So I'm going to press enter. It gets me closer to the two graphs. And it looks like if I want to be inside of the thing and outside of that other thing, I'm looking at a very small piece here. It's smaller than my graph, what my graph drew, my attempted graph at it. So I'm only looking at a small piece over here. So I kind of want to find that intersection. So I'm still zoomed in over here. I could do a trace, or I think one of the other cool features of the graphing calculator is right above trace it says calc, as in not calculus, but calculate. So I'm going to select that and see if I can find the intersection. Oh, there's no intersection here. Never mind.
That's only there when you're doing
X and Y.
Yeah.
Yeah. So what I want to do is I want to figure out where this is going to lead me to, and I need to, I mean, you can kind of guess at your angles, or you can do it mathematically, set them equal to each other. But just by inspection, it's kind of clear that I'm tracing right now, that when an angle of theta, I'm hitting both of those graphs. And then as I move along, oops, as I take my steps, I'm going to get this, which is theta of about 0.5. So I don't know how that would translate into radians. 0.5, between 0.5 and 0.6 is probably the intersection that we're looking for. Okay, so I need those two values of theta because those are going to end up being my limits of integration. All right, this is a good picture. This is a piece of the picture. So to actually find those two numbers, I know that theta is 0 is going to be an important point, and then I need to figure out what this theta is equal to. So what I could do is I could set those two things equal to each other. So to find the intersection, you get 1 plus cosine of 2 theta is equal to 2 minus sine theta. So I set these two functions equal to each other, and I'm going to solve for theta, try to at least. It's going to be easy? No. So cosine 2 theta minus sine plus sine theta is equal to 1. Now, sorry to do this, but there's a lot of trig functions that would be helpful for this. And the cosine 2 theta has a special trig function that's associated with it. You guys know? Yeah, so we want a bunch of signs in it because we have another sign in here. So if we can, cosine 2 theta is a double angle formula for cosine that has 3 different formulas that you can use. And they all involve sine and or cosine squared. So what was it again? 1 minus 2 sine squared theta. So now at this point you want to, if it's going to remain a quadratic, you want to bring everything on the one side, set it equal to 0. But if, in this case, the 1's cancel, that's good news because now you can factor out some stuff. So we got minus 2 sine squared theta plus sine theta. And if we factor out a sine, so we got sine theta times minus 2 sine theta plus 1 equals 0. And we got sine theta is equal to 0, or I guess let's solve for sine here. Negative, positive, so positive 1/2. All right, so what do we have here? We have a bunch of angles. Theta is equal to 0, pi, 2 pi. So any multiple of pi would work for this. We're looking at my graph. I want to just be in the first quadrant, so I know I can eliminate some of these other ones, but theta is equal to 0. Sure, going to be important for me. And then the other one is sine is equal to 1/2, so theta is equal to pi over 6. And technically it's equal to sine is, what is it, 5 pi over 6. So this has the pi over 6 plus n pi or something like that, and 5 pi over 6 plus something. But you know that all those other ones are not important, and all we really care about is the pi over 6. So that's that number over here, that's that angle, pi over 6. Okay, yeah. Oh, yeah, because there's another one. So when we set up the integral, we'll multiply times 2. All right. So now we're almost ready to set up the integral, except do you remember the formula for finding the area in polar coordinates? So S is equal to, was it S or A? A equals what? What? So alpha and beta, whatever. But here it's a difference between two areas. So you imagine subtracting this and then doing whatever else we need to do. So it's kind of like the washer method in calculus, where you have to subtract the two things. So your area in this problem is going to be, area is going to be 2 times, because there's 2 of them. And then the formula says a 1/2, so the 2 and 1/2 cancel. You're integrating from 0 to pi over 6, which we got. And then we got one radius squared minus another radius squared. So just have to remember which one's the outer function. The outer function, is the figure 8, or the infinity symbol. So it's going to be 1 plus cosine 2 theta squared minus, running out of room. I'll just say minus. And then the inner function is 2 minus sine theta d theta. So if you had more time, or if this was a take-home test or something like that, you can take a look at this and be able to crank out the integral either by hand or by computer. But this is probably all I want. And I prefer that you don't simplify this, FOIL it out and do all kinds of stuff, because it's going to keep me from looking at what I need to see. The simplified version is not the kind of like the raw version. So I'd rather see it like this than simplified anymore. Okay, any questions? All right, so that is 2B. All right, let's take a look at 3. Conic sections. Find an equation of a parabola with focus 2, 1 and a directrix x is equal to 4, and then graph it. So we have a focus of 2, 1, directrix x is equal to -4. So x, 1, 2, 3, 4. It's your directrix. The focus is 2, 1, 1, 2, 1 up here. So from here you should be able to find your vertex. What's the vertex going to be? Is it going to be a fraction? Be 1, 1? 1, 2, 3, 1, 2, 3. Yeah, so -1, 1 is your vertex, and then it's going to open this way. So how does the equation of the parabola go? Let's see, y. Oh, this is a sideways parabola, so x is equal to something with a y squared. Let's fix that up again. So the center is -1, so x minus -1 is equal to a times y minus +1 squared. Are you used to putting the center point here or on the other side? There, okay. So sometimes they put a +k over here, which is the center point, and so I think it's kind of like the same way. So we got the center. Now we just need to figure out what a is equal to. And a is equal to, I don't know, 1 over 2 something. 1 over 4. C. I don't. See, this is where I would dig into my notes. What? You use P?
Which is like C, which is the distance from the vertex.
Okay. So, should we do it by the book? This distance is 3. And what do they call this? They call this P?
Yeah.
And so, A is equal to 1 over 4p. So A is equal to 1 over 4p, where p is the distance from the parabola to the directrix, or the vertex, I mean. And p is equal to 3, so that's 1 over 12, right? So x plus 1 is equal to 1/12. y minus 1 squared. So I would take that or bring the 1 over to the other side. I think this is another common way to write a parabola.
Would it be negative 1?
No. So either one of those answers would work. And again, too much simplifying makes it harder for me to grade. And when I have a hard time grading, I get mad and I take away more points and stuff. So if you just make it easy for me to grade, just get all the problems right, and it'll just be easy to grade, and you'll be happy. Okay, is this good? All right, let's see if we can fit in the next problem on the same page over here. Find an equation. Oh, the graph is right here, right? Sideways parabola. Part B, write an equation, polar coordinates of an ellipse with one focus at the origin, eccentricity at 2/3, and directrix is equal to this, and then graph it. Okay. So the directrix is a line. Since I have my graph in polar coordinates still, let's figure out what this line looks like. So you should expect this to be a graph of a line. I don't know if that was obvious, but the directrix is a straight line. And I'd just be curious whether this is a horizontal line or a vertical line, because that'll give me the orientation for the ellipse. So let's draw it. And like I said, since we have our calculator still programmed in polar mode, let's say y equals. I don't want to see those other graphs, so I'm just going to put them on unequals. I mean, I suppose I could have erased it. But I want a graph of 4 times secant. Oh, do you know how to do secant in your calculator, by the way? 1 over, right? If you press inverse and cosine, it's going to give you the arc cosine. That's not what you want. So you want to make sure you actually do the secant, which is 1 over. So I'm just going to put divide by cosine theta. And so I've zoomed in, so if I press graph, I probably won't see this graph unless it's in that small window that I just recreated. So I'm just going to rezoom, and zoom to standard usually is a good way to go. So I'll press 6 here. So that's my line. It looks like it's at 4. X is equal to 4. Okay, so that's an important piece of information for me to try to figure out how this is going to, how the graph is going to go. So let's start off with that information. We got the one focus point at the origin. Eccentricity is 2/3, and an r is equal to secant. So that's your directrix is over here. Is equal to 4 secant theta. That's the same thing as saying x is equal to 4 as your directrix line. So your ellipse is probably going to go like this. Okay? Now we can probably figure this out using the eccentricity business, but we can probably dive into the formula already. So the formula to find a polar coordinate graph of an ellipse is r is equal to, I think it's ED1 plus or minus. So we have to decide plus or minus sine or cosine. So being that this is going along the x-axis, is probably going to be a cosine. And then there's an E or a D here. E. So what you can do is you can just graph both of these and then see whether it should be a plus or a minus based on your initial sketch here. So we know that E is equal to 2/3, and we know that D, now that we found a directrix, this is supposed to be a 4, that D is equal to 4. So that gives us our constants. It's just a matter of trying to figure out what the sign is. So R is equal to 2/3 times 4 divided by 1 plus or minus, and then I'll erase one of those once I figure it out. E is 2/3 cosine theta. I think if it opens up to the side, it's a plus. But let's just graph both of them. So that's 8/3, right? So let's go back to our calculator and let's graph 8/3 divided by 1, and for now I'll put a plus and see what happens. And then there's a 2/3 constant times cosine of theta. And then just for comparison, let's graph 8/3 divided by 1, and this time I'll put a minus sign. 2/3 times cosine of theta. And just so I know the difference between these two graphs, I'll make one of them thicker. So the one with a minus sign is thicker, and we'll see how both of those compare. Well, let's graph it. We have a pretty good size window there. So the minus sign is the one that's thicker, and that's the one that looks like I don't want, because that one passes through the directrix and it's all wrong and stuff. So I would probably want this first one. So what was that? That was a plus, right? That one was a plus. So let's take out the minus sign. And then that's the plus. So we're all good with that. Okay, so this is your formula. Any questions? All right, we got the equation, we got the graph, we're all good. Next. Vectors. Do we need to go through these vectors much? Looks like we're running a little bit out of time, yeah? Sure. You guys get a sheet of notes. Write whatever you want. Write as small as you want. Right? So. Yes, 8.5 by 11, front and back. You have room for a poem in there.
That's all I'm going to write.
Sonnet, limerick. All right, let's jump to number 5, since you guys are all vector experts. Unless you guys are lines and planes expert too, and we'll jump to projectile. All right, you have a point and a plane. Find the distance between a point and a plane. So this is a formula. You can rederive it if you want. That would be fun, but in a time pressured situation like an exam, you wanna write your notes yourself so that you know exactly where the formula for the distance between a point and a plane is. If you Xerox somebody else's notes and then they put their equation of the point and the plane somewhere where you're not going to be able to find it during the test, that's useless. So the exercise is for you to write your own notes so that you know where it is when you're looking for it. So the distance between a point and a plane is using a distance formula. And the distance formula, if you remember, is, I don't remember. So A times x0 plus b y0 plus c z0 minus d, and that's d over here. So if your equation of the plane is not written this way, you have to make sure you make that. In other words, if your equation looks like this, which sometimes is a way to write equations where everything is on one side and the other side is 0, you have to remember that your d is actually, in this case, positive 1, because your d is that number on the other side. Okay? And then you divide by, what do you divide by? Magnitude of the normal, so A, B, C. All right, so we have A is 1, B is 4, C is -3. And then so we take the dot product essentially. We got 2 plus 4 plus 0 minus 0 plus 0 minus 1. And then the magnitude of the normal is 1 plus 16 plus 9. Is that right? Yeah. And this is 26 in the bottom. And this is 5 on top. All right, that's good enough. Find the equation of a line perpendicular to PL passing through the point PT. So this is your plane, PL. This is your point, PT. And you want a line perpendicular to that. So what do you need for an equation of a line? You need a point and a direction. We have a point, and our direction is what? It's a normal vector, right? So that's a normal vector. So point is 2, 1, 0. The direction of the normal is 1, 4, -3. So your line equation is just a point plus t times the normal, or t times the direction. So I didn't say to write it in any particular form, so you can just leave it like this. If I say write it in parametric form, you would just look at each component. If I say write it in symmetric, is that symmetric form? Where you have to solve for t and set them all equal to each other, then you just need to write that in symmetric form. So in this case it doesn't say, so I think that's good. Find a point on the PL, that's the plane that's closest to PT. Ooh, that's a little trickier. So what I want to do for this last one, well, I have the drawing right here. The point closest to that, the point on the plane that's closest to the other point is that point that connects this line perpendicular with a perpendicular line, right? So I think I can use this equation and try to figure out where this equation is going to hit my graph, my line. What does that mean? That probably means that I need to set them equal to each other, so to speak. So intersection of L of t and PL. And what do I do to find the intersection of a line and a plane? I need to find the parametric form of the line. L of t is going to be written in parametric form 2 plus 1 times t. The y component is going to be 1 plus 4t. And the z component is going to be 0 minus 3t. And so I want to take those values and then plug them into the line. So my line is 1 times x. I guess I don't need to put that 1 in there. So this is your x. And then 4 times y minus 3 times z is equal to 1. So I put in these values, 2 plus t, 1 plus 4t, negative 3t. So this is just a linear thing. So t should be equal to -1, maybe. Maybe not. What's t equal to? Okay, I have to do it, huh? 2 plus t plus
Yeah.
-5/26. So I guess the only thing I know about this is that it's negative, because when we created this line, we had this line going up in that direction. So it should be a negative number. That makes sense. Now I take this negative number and put it into the line. So L of -5/26. Whatever that turns out to be. That turns out to be this thing. Okay. So you're going to have to deal with decimals or fractions or whatever, and that's why you have calculators for this exam. All right, that was okay. The next one is the baseball problem. So the baseball problem has initial velocity, your initial position. This is the home plate is 0, 0, 0, and you hit it 3 feet above, so 0, 0, 3. You're using feet, and so it's a -32 in the k direction, but then when you hit the ball, there's this curve, there's this Magnus force that makes this curve along the x-axis, it looks like. And so you want to find the velocity vector, the position vector, and then to find the maximum, and then they ask if you cleared the fence. So this I used Mathematica for this. So for this problem, you have the velocity, you have the initial velocity, initial position. You integrate once, you integrate twice, and you get the velocity vector and the position vector. So the path is the same as the position. So you got the velocity vector and position vectors. And then to find the maximum height, I didn't show the work here, but to find the maximum height, that's when the velocity in the z component is equal to 0. So we got z is equal to 15/8. You get that by solving the z component of the velocity equal to 0. And then you put that t value back into the position, and then it's going to tell you your x and your y and your z, but it's just looking for the height, so you find your z value. Does it clear the fence? So this is the distance. This is not a very good drawing, but if you imagine, let's just get a picture of this in our notes. So the drawing, I had to tilt the drawing so you can view the fence around, but if you take a look at this and the fence going around, this is where you hit the ball and your path follows a particular thing. So you want to know if it cleared the fence, or if it hit the fence, or if it went below the fence. So what you want to do is you want to find the distance, 380 feet. So the distance from the home plate to the fence is 380 feet. And then so if you look at just your x and your y components, so if you look at the ground, x, y distance from home plate, then you're looking at just a two-dimensional distance, kind of like the shadow of the ball. So the xy component distance, when that's equal to 12, that's going to give me the time that the ball has traveled this many feet away on the xy plane, the shadow of the ball. And so what you want to do is you want to take that time and put it into the height. So z of 3.59. And that tells you how high the ball is. So it looks like the ball, this wasn't a good number. Looks like the ball was like 12 feet high, I think, is when I had it set up. So that's how you would find whether it clears the ball. But the main part of this is coming up with the main part of this is coming up with the velocity and the position functions based on your acceleration, your initial velocity, initial position. And once you have your velocity and position functions, you can answer a bunch of other types of questions, like when it's going to hit the ground or what the highest point is. Okay? All right. So the solutions are not posted. The solutions for, I'm just looking at the solutions for that last one is not very clear, but I hope you guys can work it out and talk to other people about it. But we skipped over number 5 or number 4, the vectors page, but the solutions to that is all here. Okay? All right, you got the outline, you got a sheet of notes to work on, you got the review, and you got the solutions to the review. So I hope that's enough for you to do okay on the test tomorrow. It's a matter of spending time and quality time to study. Bring your calculators. Good luck.